Hello, now we are going to study the second part of the section 13.2, and this section is all about derivative and integral, and the second part is integral. So let's take a look at definition 3. The indefinite integral of the vector function integral of a vector function RT respect to t is the set of all antiderivatives of R. So we define by this way, denoted by, let's see, it's same as indefinite integral before, but here we write down this as vector and dt, and t is the variable. Okay, and in general, if capital R is any antiderivative, and then we write down this as RT plus C, and here R is any antiderivative. Okay, and the calculation of RT dt is just we do calculation of each component function, like xt dt, integral yt dt, integral of zt dt. Okay, now let's take a look at the example. Here a vector function is given, RT, which is 2 cosine t I sine plus sine t j plus 2tk. Let's find the integral of this vector function RT dt. So we are going to do just 2 cosine t dti, and integral second component sine t dt j, and integral of 2t dt times k. And we just evaluate each integral. So integral of 2 cosine should be negative 2 sine t I, and sine integral should be, okay, here the first one is plus, and this is negative cosine t j and plus t squared k. And because we know it's same as indefinite integral, we need to add a c because it's general. That means include all antiderivatives. Now let's take a look at this exercise problem. Okay, so if we want to calculate a definite integral, for example, 0 to pi over 2, like this RT dt, how to evaluate? We just do the same thing, plug in the upper bound and the lower bound. So it's going to be like 2 sine pi over 2i minus cosine pi over 2j plus pi over 2 square and k. So this is when we plug in pi over 2, and then we plug in 0. So it's like 2 sine 0i cosine 0j plus 0 square k. Okay, and let's simplify. This equals to 2i, and this is 0, and plus pi square over 4k, and minus here 0, and plus j, because this equals 1, right? And let's rewrite this equals 2i plus j plus pi square over 4k. This is the definite integral. Now let's take a look at this exercise. Evaluate 0 to pi cosine ti. Okay, and dt. Here is the solution. Take an integral of each term. Tj t squared k 0 to pi, plug in. And actually when we plug in 0 to any term, they are just 0. Same pi 0. So the final answer is just pi j minus pi squared k. Okay, you can check this answer. So here I give you a summary. How to do the integral, indefinite integral of RT dt equals integral of xt dti, integral of, if RT is given by xti ytj ztk. So just take each component j, integral of zt dtk. So this is the indefinite integral, and definite integral from a to b rt dt, this just equals rt a to b, and which is rb minus ra. And what is r? R is the antiderivative of rt, vector function. So here there are just the two formulas we need to know for the integral. Next, we want to see the application. Okay, when do we use the integral of the function? Example 5. So right now we know the acceleration, and we try to find the position. Okay, so let's take a look. The acceleration. For the calculator is given by this one, at, and -3 cosine ti minus 3 sine tj plus 2k. So we know this is in 3D, right? Because 3 components. Okay, and now we know initially the calculator departs from the point 300. So okay, when we read the problem, can you translate this word into math formula or equation? And what is given information? You can think about that. And with velocity is 3j. So we want to find the position function. Position as a function of t. Okay, so now let's read the problem. The acceleration is given. Let's write down the information. At, which is -3 cosine ti minus 3 sine tj plus 2k, right? And the second word, we know initially. So initially means what? So when we talk about initially, that means at beginning, right? At beginning, that means t equals 0. So sometimes we also call this initial condition. I don't know if you learned this in physics class or not. So this is called the initial condition. Initially depart from this point. So this point is what? Actually, that is position at 0. Okay, position vector. So position start from that point, right? So let's write down 3, 0, 0. And with initially with this velocity. So that means what? Initial velocity. Okay, so initial velocity. So this is the velocity when time is 0. When t equals 0. So you can also say when t equals 0, that means initially. And the vt equals, 3j, that means what? Means 0 for the I, and the 3 and the k component is also 0. Something like that, right? And usually we call this initial value problem. If you learned Calculus 2, we should already did some initial value problem. Initial value problem we did before is like dy dx equals something, and we know y0 equals something, or y1, and we find the y value. Okay, y function, something like that. Initial value problem. Now let's see. So we are going to find what? We are going to, the problem find the position vector. So the goal for this problem, we want to find the ST. So, but before we find the ST, we should know what is AT, how we get AT. AT actually is the second derivative of ST. Is that right? Okay. So our, the idea to do this problem, how to do this problem, we're going to find VT using the given AT, and then we find the ST by using velocity. Then we want to find, so this is the idea. Okay, we want to find the ST by using VT. So now let's see how to find the velocity if the acceleration is given. So velocity is the antiderivative of AT, right? Because velocity derivative is AT. Okay, and how to find the V antiderivative? So just do the integral of AT. So VT equals what? Firstly, we set up this as AT dt. Integral, that's the integral of acceleration. And then now we just do the integral of this AT. So here I just plug in. You don't have to copy this one, you can calculate it directly. So integral of -3 cosine, -3 sine t. And integral sine should be negative cosine, so it should be cosine t. And the 2 here, 2tk. And be careful, we have constant, arbitrary constant, right? So here we write down as C1, because in the you can also just write down C, doesn't matter too much. I like to do C1 and then later I use C2, but you can always use C. This is velocity function. Okay, and now we want to use the initial condition to find the C1. So which initial condition we want to use? We want to use this initial velocity. Okay, so let's see. Let's calculate V0. Plug in here V0. So it should be negative sine 0, 3 cosine 0, j, and the plus just 0 times k, right? And the plus C1, and which is given by, okay, because left side I write down IJK form, so the right side I always want to write down the IJK form. And now let's take a look. This is 0 and 0, and this is just 3j, right? So that means 3j plus C1 equals 3j. That means what? That means C1 equals 0. Depends on our initial condition. If my initial condition equals something like k, so my cy will be k, right? So depends on the initial condition. Now cy is 0 based on this condition, and now I'm going to rewrite out my vt, velocity. So my velocity is this, and the plus c1, because c1 is 0, so I don't need to write down anything. So this is our vt. Next, we are going to find st. So the procedure is totally the same thing. So we want to find the integral of vt dt. So integral of negative 3 sine t, 3 cosine tj, 2tk, actually here is 2tk, 2tk and dt. Let's evaluate this integral. So this should be 3 cosine ti plus 3 sine tj and plus t squared k and plus c2. Right, plus c2. And then next, we want to use the initial condition as 0 to find our c2. So s0 is given by what? It's 300 or 3i. So let's plug in, find s0. So 3 cosine 0i, 3 sine 0 j, 0 k plus c2. This is s0 when I plug in t as 0. And the initial condition is given by 3i. And this is 3i, okay? And this term is 0, and this term is 0. So 3i plus c2 equals 3i. So that means c2 is also 0. So my st, just write down the final solution, which is 3 cosine ti, 3 sine tj plus t squared k, and c2 is 0. So final answer is this one. Okay, this is called the initial value problem. So here we did a twice integral, and then by using the initial condition as 0 v0, we find the c1, c2, and then we just write down our final solution. Next, I'm going to give you the exercise. Let's try. Here I'm not going to give you the word, I just give you the problem. But you know, when you do the homework or do some other problems, you may need to translate them into those equations. So here I give you this. Do you know what's the meaning of this one? Means second derivative, right? And here r0 is given. And this kind of problem will be in the final. So this is more like physics problem. This is traditional like a initial value problem. Usually initial value problem is given by this form. So let's take a look. Second derivative is given, and we are going to find the RT. And R0 is given, so it's like a position vector. And dr dt, that is like velocity. First derivative, when t equals 0, is also given. It's like velocity, initial velocity. Here is the solution. Firstly, I calculate the first derivative, dr dt, which is integral of negative I dt. So it's like an integral of 1, which is t. So negative t I minus tj minus tk plus c1. And the initial condition is, so it should be 0, okay. dr dt when t equals 0, so which is c1 and is given by 0 vector. So that means c1 is 0. Next, we are going to find, I'm going to write down dr dt. Plug in C1, so negative I. And integral this again and find R. So RT equals integral of dt. And the integral of this one is negative t squared over 2. T squared over 2j. Okay, plus C2. And then plug in R0. R0, which is C2, and which is given by initial condition 10i plus 10j plus 10k. So that is my C2, and then I just plug in to my RT. So my RT final answer should be this one. Plus C2. C2 is 10i plus 10j plus 10k. And you know, we don't like to write down this form. We want to combine the components, i's component together. So it's negative t squared over 2 plus 10i. And the j's component together. Plus 10j over 2 plus 10k. So that is our RT final answer. Okay, so we can stop here. In another, like in 13.4, we're going to learn the motion of particles in space. So we're going to do more application of the integral. So it's like a projectile motion. So it's called, it's like if we fire a rocket. So it gives some, we have some initial velocity, some angle, and we want to see what's the highest position it can get and how far it can hit the ground. Okay, so we're going to do that later. Right now it's just a basic integral and a basic application, which is initial value problem. We can stop here.